Jupiter looks like a place you could someday visit, maybe even live above those huge swirling clouds, but that picture is way off. In this video, you and I are going straight into what Jupiter really is, what actually happens if you try to move there, and why the phrase living on Jupiter doesn't survive even the first serious look. Here's the core problem with trying to live on Jupiter. There is nowhere to stand at all. You're used to planets being big versions of what you know on Earth. Air above, ground below, maybe water in between. Jupiter breaks that picture. It's made mostly of hydrogen and helium, gas all the way down from the cloud tops into a deep layer of super compressed fluid. There is no sharp point where you go from air to rock. There is no continent, no seafloor, no crust you can drill into. When scientists talk about Jupiter's surface, they're not talking about solid ground. They're talking about a pressure level, the place where the air pressure is about 1 bar, the same as sea level on Earth. That's useful for science, but it is useless for building a city. So what actually happens if you try to land a ship on Jupiter, not in a sci-fi painting, but with real physics? You drop into the upper atmosphere, you slow down. The pressure around you climbs until your instruments read 1 bar, and your brain wants to call this the surface. But the ship doesn't stop. There is no impact, no touchdown, you just keep sinking. The gas outside gets thicker, more like a heavy fog, then like a very thin fluid. You pass through cloud layers of ammonia, water and other chemicals, but there is still nothing solid under you. Gravity is pulling you down, but nothing is pushing back from below. If your engines fail, you don't fall for a few minutes and hit ground, you fall indefinitely into denser and hotter layers until the structure of your ship fails. That raises a simple question. If there is no ground, why do you see numbers like surface gravity about 2.5 times Earth's listed for Jupiter? How can you talk about surface gravity on a planet with no surface? The answer is again that scientists pick that 1 bar level and pretend it's a surface for convenience. At that height, the downward pull of gravity is around 25 meters per second squared, which is roughly 2.5 times what you feel on Earth. So if you weigh 80 kilograms on Earth, about 176 pounds, at that level on Jupiter your body would feel like 200 kilograms, about 440 pounds. That's a useful comparison, but it hides the real situation. You're not standing on a floor, you're hanging inside a moving fluid. Saying surface gravity, there is like saying sidewalk gravity in the middle of a cloud. It sounds solid, but there is nothing under your feet. If that fake surface doesn't work, maybe you think you just need to go deeper, go down far enough, and surely you must eventually hit some kind of solid layer. So what does that descent look like as you continue? After you pass a few hundred kilometers, a few hundred miles below the visible clouds, the distinction between gas and liquid starts to disappear. The hydrogen around you is compressed so much that it behaves like a supercritical fluid, not a normal gas, not a normal liquid, but something in between. The density goes up, the pressure reaches tens, then hundreds, then thousands of bars. For comparison, a few hundred meters under Earth's oceans might give you a few tens of bars. Jupiter ramps past that very quickly. Keep going, and the fluid layer turns into what we call metallic hydrogen. Under pressures of millions of bars and very high temperatures, hydrogen atoms are squeezed so tightly that their electrons can move freely, like in a piece of metal. This material can conduct electricity extremely well and is believed to generate much of Jupiter's magnetic field. But for you, as someone hoping to find ground, this is not a solid platform. It is still fluid, still moving, still crushing. The deeper you descend, the hotter it gets, climbing into thousands of degrees Celsius, thousands of degrees Fahrenheit. Any real ship we could build is being pushed on from all sides with unimaginable force, while being heated far beyond the melting point of common metals. Before you ever touch anything solid, if anything solid is even reachable, your hull buckles, your systems fail, and the whole vehicle is destroyed. At this point you might ask, alright, but what about the core? Doesn't Jupiter have a rocky core at the centre that we could eventually reach? The honest answer is that we are not fully sure what that core looks like. Many models say there is a central region with heavier elements, rock and ice, maybe several times the mass of Earth. Other models suggest that this core is fuzzy, partly dissolved into the surrounding metallic hydrogen spread out over a large region instead of being a neat solid ball. But here is the key point. Whatever is down there is buried under so much overlying hydrogen fluid that, from a human point of view, it might as well not exist. Think of Earth's inner core, where pressures reach millions of times our surface pressure, and temperatures are over 5,000 degrees Celsius, about 9,000 degrees Fahrenheit. Now push those numbers even higher. Near Jupiter's centre, the pressure is expected to be tens of millions of bars, and temperatures around 24,000 degrees Celsius, over 43,000 degrees Fahrenheit. Even if there is rock, it is likely mixed into that extreme environment, not sitting as exposed solid ground. You cannot dig into it, you cannot land on it, you cannot even send a probe there with our current technology. Any base on the core is not a serious engineering idea, it's just a fantasy phrase. So if landing is impossible and the core is unreachable, you might try one last idea. What if you never land at all? What if you live in the atmosphere in a floating city? That sounds like a clever workaround. You stop caring about ground, you pick a level where the pressure and temperature are closer to something we can handle, and you stay there. This kind of idea has been studied for Venus, where the air is thick and heavy, and you can float with balloons filled with lighter gas. But Jupiter gives you a very different set of numbers. The atmosphere is made mostly of hydrogen with some helium. Hydrogen is the lightest common gas in the universe. On Earth, you can fill a balloon with hydrogen, and it floats because our air is heavier, made mostly of nitrogen and oxygen. On Jupiter, you're already in hydrogen. If you fill your habitat with helium, or with warm hydrogen, you only get a very small difference in density compared to the outside. That means, to lift a certain mass, you need a much bigger balloon than you would on Earth. Now add the fact that gravity at those levels is about 2.5 times stronger than on Earth. Every ton of mass feels like 2.5 tons. The structure has to be enormous just to keep itself afloat, and every extra kilogram of shielding, machinery and life support gets multiplied by that stronger gravity. Even if you somehow build that huge floating structure, you still need to stay in one piece inside Jupiter's weather. The winds in the upper atmosphere can reach hundreds of kilometers per hour, hundreds of miles per hour in long, powerful jet streams that wrap around the planet. There are vertical currents that push gas up and down. There are strong shear layers where the wind speed changes sharply with height or latitude. Your floating city is constantly being pushed, tilted, stretched and shaken. You have no mountain to anchor to, no ground to dig foundations into. You only have thrusters and control systems fighting the air every second, burning energy just to hold position. On top of that, the gas around you is not clean. There are clouds of ammonia, water and other chemicals that are harsh on metals, seals and electronics. Over years, that mix would corrode many materials, weaken joints and eat away protective coatings. Any external surface you expose has to be engineered for chemical attack as well as for pressure and mechanical stress. For a short robotic mission, that is already hard. For a permanent human habitat, it becomes a never-ending maintenance fight. So when you put all of this together, the picture is simple but unforgiving. Jupiter does not offer you a surface to stand on, a seabed to build on, or a calm, stable layer to float in. Its surface is just a convenient pressure number. Its interior is a crushing, superheated ocean of exotic hydrogen, and its atmosphere gives you almost no buoyant advantage while beating you up with strong gravity and violent winds. And here is the twist. Even if Jupiter somehow handed you a solid platform tomorrow, a giant slab of rock suspended in the clouds, the next problem you would face on day one is just as bad, the strength of Jupiter's gravity itself, and what living under about 2.5 G would do to your body, your buildings, and your rockets. Jupiter doesn't just refuse to give you a surface, it also hits you with gravity that your body was never built for. At the level where the pressure feels like normal sea level on Earth, the downward pull is about 2.5 times what you're used to, and that single number quietly breaks almost everything you'd need to live there. So first, what does that actually feel like? Not as a statistic, but inside your own body. At the cloud tops, near that 1 bar level, gravity is about 24.79 meters per second squared, roughly 2.5 g if you're 80 kilograms on Earth, about 176 pounds. Your body now acts like 200 kilograms, around 440 pounds. Your heart has to push blood through a system that suddenly weighs 2.5 times more. Your leg muscles are carrying a load they were never trained for. Your spine is compressed harder with every step. Just standing up feels like hard exercise. Walking across a room feels like slogging uphill with a heavy backpack. And any kind of lifting goes from manageable to I need a machine for this very fast. That means daily life changes from moving around easily to calculating every movement. You don't casually jump, you don't run for fun, you don't climb stairs unless you really have to. Your joints wear out faster, your cartilage is under more stress, your blood pressure has to run higher just to keep your brain supplied. And that's assuming you're healthy, young and in good shape. If you bring kids, older people, or anyone with heart or circulation problems into 2.5 G and ask them to live there long term, you're basically running a continuous stress test on their bodies. If your own body is working that hard just to exist, think about what that does to anything you build. On Jupiter, every structure is carrying 2.5 times the load that same structure would feel on Earth. Take a habitat that has a mass of 100 tons. On Earth, its weight is already serious, but we know how to handle it. In Jupiter's gravity, that same 100 tons effectively load supports like 250 tons. Every beam, every column, every cable is being pulled on harder. So you don't just scale things up a bit, you have to redesign almost every part of your engineering. Floor supports, pressure hulls, airlocks, docking clamps, all of it has to be thicker, stronger, and usually heavier, which then adds even more load. It's a loop. More gravity means stronger structure. Stronger structure means more mass. More mass means even more load from gravity. You can't cheat that with clever design forever. At some point you're hauling huge amounts of material just to make a building stand up. And that's before you add extra mass for radiation shielding, life support machinery, and fuel tanks. Now look at vehicles. Any lander, any atmospheric craft, any hovering platform has to fight that same 2.5 G all the time. Engines have to push harder just to hold you at a fixed altitude. If something goes wrong and you need to pull away from danger quickly, the thrust you need is brutal. The crew feels that as high acceleration, lots of G, stacking on top of an already heavy baseline. Short bursts of high G are doable for trained people, but if every takeoff and landing punches you with intense forces, accident risk climbs, and human tolerance is pushed to its limits. Then there's the really ugly part of Jupiter's gravity, the depth of the gravity well itself. At the cloud tops, Jupiter's escape speed is at about 59.5 kilometers per second, roughly 214,000 kilometers per hour, about 133,000 miles per hour. For comparison, to leave Earth you only need about 11.2 kilometers per second. That means to get out of Jupiter's grip you need more than 5 times the speed you need to escape Earth. Energy scales with the square of speed, so when you multiply the speed by a bit over 5, the energy doesn't just go up 5 times, it explodes by around 25 times. In simple terms, getting a ship out of Jupiter's gravity well costs roughly 25 times more energy than the same mass leaving Earth, roughly, depending on details. Fuel isn't just more expensive, because it becomes the main thing you're hauling. Your rockets get huge, your fuel tanks get gigantic, and your payload, the part that actually carries people and equipment, shrinks. This destroys the idea of easy supply runs or emergency evacuation. On Earth, we already treat escape velocity as a big engineering obstacle. Around Jupiter, you're at the bottom of a deep, steep well. Every trip up that well is a massive operation, and any mistake on the way out is probably not recoverable. Living there doesn't just mean surviving the environment, it means accepting that leaving is incredibly difficult every single time. So what about your body? Not during a quick launch, but living under about 2.5 G day after day, year after year. Human centrifuge tests show we can tolerate a few G for short periods, especially lying down with blood flowing along the right direction. Fighter pilots can push up to around 9 G for seconds, using special suits that squeeze their legs and abdomen. plus breathing and muscle tensing techniques, but that's short term, not a lifestyle. At 2.5G, your heart has to work harder all the time just to move blood upwards. Blood pools in your legs and lower body more easily. Your veins and valves face more strain. Your spine is compressed more each day, so discs between vertebrae wear down faster. Your knees, hips, and ankles feel a constant overload. So joint damage and arthritis-type problems would likely show up sooner and more severely. Even your internal organs shift and press down more inside your body. Without very heavy medical support, specialized training, and probably genetic or surgical changes, we don't know how to do yet. It's doubtful that humans could live full, healthy lifetimes in that environment. Sleep, recovery, and exercise all change too. On Earth, normal rest lets your body repair itself overnight. At 2.5G, even lying in bed loads your tissues more. Your heart never gets an easy mode. You would need constant, carefully managed exercise just to keep circulation working, and even that might not offset the chronic stress. We don't have long-term data, because no one has lived in sustained high gravity, but everything we know from short tests points in the same direction. Long-term 2.5G is bad news. People sometimes talk about Jupiter as if it were just a heavier version of home, the same basic idea as Earth, just scaled up. That picture is wrong in a way that matters for survival. A world with a deeper gravity well is not just a bit tougher, it changes the whole game. Rockets have to be far more powerful, structures have to be way stronger, humans are constantly under physical stress, and the cost of leaving or rescuing anyone explodes. On a bigger, denser planet with a solid surface, you at least get ground in return for that stronger gravity. On Jupiter, you don't even get that. You're dealing with 2.5G in a place that has no floor, brutal escape speeds, and an atmosphere that wants to crush and cook your vehicles as soon as they slip too deep. The gravity doesn't just weigh you down, it traps you. And the scary part is, this still isn't the full story, because even if you somehow upgraded your rockets, reinforced your buildings, and medicated your crew to handle the extra weight, the next layer of Jupiter's environment is waiting underneath. The pressure that climbs from normal air to deep ocean crush in just a short drop. Pressure on Jupiter is the part that sounds harmless at first, because someone can tell you, up at the cloud tops it's just like sea level on Earth, and that feels normal, right? 1 bar of pressure, same as at a beach on Earth, you think, okay, that's fine, but that 1 number hides a nasty trap, because on Jupiter, that comfortable point is just a thin layer, and a short drop below it turns into a one-way dive into crushing force. At that 1 bar level, your body feels at home. If you stepped out in a suit that could handle the cold and the chemistry, your lungs would see a familiar pressure from the inside, your eardrums wouldn't burst, your blood vessels wouldn't explode. It feels like a safe reference point. The problem is you can't stay pinned at that exact level without constant help. As soon as your vehicle loses lift or the thrust and starts to sink, the pressure ramps up very fast. You're not talking about a gentle, slow increase, you're talking about tens of kilometers of descent turning into many times Earth's sea level pressure. We actually tested this the hard way with the Galileo probe. It entered Jupiter's atmosphere at very high speed, used a heat shield to survive the initial entry, then deployed a parachute and started sending data as it fell. For about an hour, everything worked. During that time, it went from almost zero pressure at the edge of space up to around 22 bars, roughly what you get 200 to 300 meters under Earth's oceans. After that, contact stopped. The heat and pressure simply went beyond what the probe was built to handle. So a tough one-way robotic capsule made to be sacrificed only lasted about an hour before the environment shredded it. That gives you a very clear message. This is not a place where you casually send people down for a look. So what happens if you don't stop at 22 bars? What if you keep going? The deeper you fall, the faster the pressure multiplies. At first, hydrogen and helium still act like gas, just denser. Then you hit a regime where the gas becomes a supercritical fluid. That's a technical term for something that is not a normal gas and not a normal liquid. It's a state where the difference between the two disappears. It can be as dense as a liquid but fill space like a gas. Around there, the pressure has climbed to hundreds of bars, then thousands. For reference, a modern deep-sea submersible on Earth might see 1,000 bars at the very bottom of the deepest trenches, and that's already extreme engineering. Go further, and you eventually enter the region where hydrogen becomes metallic hydrogen. In that zone, the pressure is in the megabar range, which means millions of bars, millions of times the air pressure you feel at sea level on Earth. At that point, materials behave very differently from what we're used to. The strongest steels and titanium alloys we rely on would not stay rigid. They would deform and flow over time. Under that kind of load and heat, they basically act like very slow, very hot putty. There is no straightforward way, with technology we know now, to build a hull that shrugs off millions of bars and thousands of degrees for any useful length of time. So that's what happens to metal and composites. But what about your actual body in this kind of pressure gradient? If you dropped a human even a short distance below the safe region without protection, the effects are brutal. Your lungs are filled with air at 1 bar. As external pressure climbs, the air inside gets squeezed. If the outside pressure rises faster than you can equalize, your lungs can collapse. Any pockets of gas in your ears, sinuses, and intestines are also compressed, causing intense pain, tissue damage, and internal bleeding. This is the same physics that makes divers on Earth worry about pressure sickness, but cranked up far beyond anything you see in normal diving. And it's not just pressure. In the upper layers, the temperature can be around minus 140 or 150 degrees Celsius, roughly minus 230 degrees Fahrenheit. That is deep freezer cold. Surrounded by hydrogen and helium, which conduct heat very efficiently, your suit or hull loses heat quickly. Then as you sink, the temperature swings the other way. Every kilometre down adds more heat, until you're dealing with hundreds and then thousands of degrees Celsius. There is no comfortable band where pressure and temperature line up nicely. Either the pressure is survivable but the cold is extreme, or you've reached warm regions where the pressure is already fatal. Now, think about what kind of machine you would need to carry humans down through this. You'd need something that's part deep-sea submarine and part re-entry capsule. It has to handle high-speed entry at the top with shock heating and high winds, and then smoothly transition into a pressure vessel that stays intact as the outside pressure jumps by tens or hundreds of bars every few minutes. Winds in Jupiter's atmosphere can be supersonic in parts, so the hull isn't just sitting in still fluid, it's getting hammered by sideways forces as well as squeezed from all directions. For Galileo, engineers could say, this probe only needs to survive for about an hour, then it can die. They built it strong enough for a one-way trip to 22 bars, and even that was a hard challenge. Now imagine upping that to a vehicle that carries people, has life support, has systems redundancy, and then ask it not just to go down, but to come back up. The safety margins multiply, the mass multiplies, and the chances of a single failure killing everyone go way up. With our current understanding and materials, designing a reusable human-rated descent and ascent craft for Jupiter is not just hard, it's basically in the sci-fi only column. Maybe you think, okay, then don't go deep, just stay in a narrow layer where the pressure is a few bars, maybe the temperature is around minus 50 degrees Celsius, which is awful but manageable with good suits and heating. The problem is, Jupiter doesn't give you a stable, quiet shell like that. The atmosphere is strongly convective, which means gas is constantly rising and sinking. Jet streams slide past each other at different speeds. Large storms punch material up and drag material down. If you place a floating habitat at some altitude, it isn't sitting on an invisible shelf. It's embedded in moving fluid that wants to carry it up and down. Local heating, cooling, and weather systems will keep trying to push it out of that sweet spot. To stay at the same pressure level, you need constant active control, changing buoyancy, or running thrusters. If you drift downward, pressure climbs and your structure gets more stressed. Drift upward, and the outside gets colder and thinner, and your buoyancy changes again. There is no calm, long-term habitable band that just sits there waiting for you to plug in a city. So the descent profile on Jupiter is simple but ugly. Start in a layer that tricks you into feeling safe, drop only a short distance, and suddenly you're stacking up multiple Earth-ocean pressures, freezing temperatures, then furnace temperatures, and material stresses beyond anything in normal engineering. And here's the key point, even if you somehow mastered that, Even if you built the perfect pressure hull and flew it perfectly inside this churning fluid, you would still be fighting something you can't armor against with metal: the huge swings in temperature from the top to the deep interior. Pressure alone is enough to crush you, but when you mix that with cold that shatters metal and heat that melts it, Jupiter turns from dangerous to basically off limits for human descent. Temperature on Jupiter doesn't just make things uncomfortable, it completely destroys the idea that there could ever be a safe middle zone where humans might live. You're dealing with a world where the sky can freeze metals, and the deep interior runs hotter than the surface of a star, and there is no stable layer in between where things calm down. Start at the top, where those bright cloud bands sit. In the upper atmosphere, temperatures are around -145 degrees Celsius, about -230 degrees Fahrenheit. That is not just very cold, that is cryogenic, liquid nitrogen level cold. At those temperatures, a lot of gases you think of as normal air components can turn into ices, and many metals become brittle. They stop bending and start snapping. Your spacesuit is no longer just fighting vacuum, it's fighting an environment that will pull heat out of you faster than any winter storm on Earth. A normal suit or habitat radiates waste heat and vents warm air or water vapor to keep internal systems cool. On Jupiter's cloud tops, that waste heat is sucked away immediately. Any vented moisture will condense or freeze almost instantly, forming ice on valves and outlets. Hydrogen and helium, the main gases up there, conduct heat well enough that they strip warmth from exposed surfaces very fast. So your life support system is in a constant emergency, always pumping energy into heaters just to keep things at survivable temperatures inside. Every joint, every flexible seal, every exposed metal part has to be designed not to crack when the temperature plunges and the material contracts. You might think, fine, the top is brutally cold, but as you go down, maybe you can find a Goldilocks layer where the temperature becomes reasonable, something close to room temperature. The problem is, the direction of change is simple. Deeper means hotter, always. As you descend, compression and internal heat raise the temperature steadily. There's no dip or plateau that hangs out near 20 degrees Celsius, around 68 degrees Fahrenheit, in a pressure range that humans can tolerate. Go down far enough that hydrogen stops acting like a thin gas and turns into a dense fluid, and you're already at temperatures of thousands of degrees Celsius, thousands of degrees Fahrenheit. Down near the core region, models put the temperature around 24,000 degrees Celsius, roughly 43,000 degrees Fahrenheit. That's hotter than the surface of the Sun, which sits at about 5,500 degrees Celsius. So this one world gives you upper layers colder than anything on Antarctica's worst night, and deep layers hotter than a star's visible surface. From top to bottom, the thermometer never does you a favour. So maybe you try to be clever and say, okay, let's forget the extremes. What I want is a narrow band where pressure and temperature together look good. Maybe a spot where it's a few bars of pressure and something like human-friendly temperatures. You can find exoplanets in models where that kind of layer might exist, where gas temperatures hover around 20 or 30 degrees Celsius, at pressures only a few times Earth's sea level. But Jupiter does not offer that kind of band for free. Where the pressure is not insane, up near the top the temperature is brutally low. Your main problem there is freezing and brittleness, not overheating, where the temperature gets into the range where liquid water could in theory exist. The pressure is already high enough to crush normal materials and strip apart molecules. Water itself under those conditions doesn't behave like the liquid you drink, it becomes supercritical, more like a very hot, very dense fluid with no clear surface. And that's if it even survives at all in the mix with hydrogen and helium. In other words, you never get a region where both the temperature and the pressure are gentle at the same time. If one is friendly, the other is trying to kill you, you don't have a natural shirt sleeve layer where you can put a lightly shielded habitat and relax. Any human base has to create its own microclimate from scratch with heavy walls, heating, cooling, and strict control over altitude. And that base is still surrounded by layers that are either freezing or fiery. Now add one more problem that people often forget. Jupiter is not just being heated from the outside by the Sun, it is heating itself from the inside. Earth mostly cools off into space, sunlight warms the surface, the planet radiates heat back out, and the net balance is pretty close. Jupiter, on the other hand, radiates more energy than it receives from the Sun. It is still slowly contracting under its own gravity, a process called gravitational contraction, and that releases heat from the deep interior. That internal heat keeps the lower layers hot and helps drive convection, big up and down motions of gas that feed the weather patterns you see on the cloud tops. So even if you were to block out sunlight completely, hide your habitat under a sunshade, or stay on Jupiter's night side, you still have to deal with heat coming from below, carried up by rising fluid and radiated as infrared energy. You cannot turn off the planet by cutting off starlight, the furnace is built in. Put all this together and think about what it means for your technology, for any structure you try to keep floating or hovering in that atmosphere. You're surrounded by huge vertical temperature gradients. Move upward a bit and the outside air gets colder. Your hull and structure contract. Mechanical parts tighten. Some materials become more brittle. Gaps can open up in seals. Lubricants can thicken. Batteries and electronics can lose performance. Move downward a bit and the opposite happens. Everything heats and expands, gaps close, stresses shift, and delicate components risk overheating. Even if those temperature changes are only tens of degrees up or down over the range your habitat moves, repeating that cycle over and over causes fatigue. Metals develop micro cracks, composite materials delaminate, solder joints in circuit boards weaken, rubber seals harden and then soften, losing their shape. Your engineers are now fighting not just one extreme but constant cycling between extremes, like baking the structure and then flash cooling it, again and again. Cooling systems also get trapped in a nasty corner. In the cold upper layers, you have to dump waste heat into an environment that is already freezing. That sounds easy, but you have to control it so you don't overcool vital systems. In the warmer lower layers, your external radiators are facing hotter surroundings, so they become less effective just when you need them more. Parts of your habitat might end up too cold while others are too hot, all at the same time, because the outside conditions are changing fast as you drift. You can picture it this way. Your habitat is being asked to behave like a spacecraft designed for deep space, a polar base in Antarctic winter, and a high-temperature industrial furnace all in one package, with no real downtime for maintenance. Temperature is not just a number on a screen, it is the direct attack on your materials, your hardware, and your safety margins from both ends of the scale. And remember, all of this is happening in an atmosphere that is not still. It's moving fast, it's churning, it's full of shear and turbulence. So while you are trying to keep your people warm but not cooked, your computers cool but not frozen, and your metal strong but not brittle, the air around you is slamming into your hull at hundreds of kilometers per hour. The temperature problem never hits you alone. It always arrives packaged together with wild winds and giant storms, and that's the next layer of trouble, because on Jupiter, even the air you're floating in is moving at speeds that start to look more like jet fighters than gentle breezes. How do you build a peaceful sky city in a place where normal wind speed is already in disaster territory back on Earth? On Jupiter, the atmosphere doesn't just move, it rips, and that changes your floating habitat from a calm platform into something that's being pushed, twisted, and shaken every second it exists. Start with the basic numbers. Around the equator, Jupiter's jet streams can reach about 150 meters per second, roughly 540 kilometers per hour, about 335 miles per hour. That is well into hurricane strength on Earth, not as a rare event, but as a baseline, the normal background wind. And that's just the large-scale jets. Local storms and vortices can push winds even higher, with sharp gusts and swirling flows. Drop any kind of floating station into that, and it doesn't behave like a calm balloon over a quiet field. The surrounding gas is hitting it at hundreds of kilometers per hour from slightly different directions, with speeds that change over time. Keeping one side pointed forward suddenly becomes a full-time job for your attitude control systems. Thrusters have to fire constantly to resist spin, to stop the station from flipping, to keep solar panels or radiators pointed where they need to be. If your structure relies on buoyancy alone, it will drift with the flow, but the flow itself isn't uniform. One side might be in slightly faster air, another in slower air. That creates torque, a twisting force trying to rotate and bend the entire platform. You can't just park the habitat and trust that the air will stay gentle. Even if the winds stay roughly the same speed, the small changes are enough to strain joints, supports, and cables every single minute. Now scale up from regular winds to the big storm that everyone knows, the Great Red Spot. This is not just a big storm by Earth standards, it is a storm at least as wide as Earth itself, roughly 16,000 kilometers across. It's a gigantic rotating system that has been active for centuries. The wind speeds around its edges can reach hundreds of kilometers per hour, and the internal flows are complex, with rising and sinking gas, eddies, and smaller vortices embedded inside the larger one. Imagine saying local bad weather, and meaning a structure the size of your whole planet, sitting there in the atmosphere, changing shape but never really shutting down. You don't evacuate to the next region and wait for it to pass, because it doesn't pass in any human timescale. It just drifts and evolves. Any habitat that gets close has to plan around the edge of that storm like it would around a moving continent of turbulence. So you might decide, fine, avoid the red spot, stay in calmer bands. But Jupiter's atmosphere isn't a single layer. It's built from stacked jet streams at different latitudes and altitudes, each with its own speed and direction. That creates shear, where one layer of gas is sliding past another. Shear is dangerous because it creates turbulence right at the boundary. For a floating base, that means part of your structure can be in a slightly faster layer, while another part is in a slower layer, and those differences pull your frame in opposite directions at once. If your platform is tall, or if it has long tethers or extended modules, the top and bottom can be in noticeably different wind regimes. That leads to bending loads, oscillations, and mechanical fatigue. To fight that, you need active control systems changing buoyancy or firing thrusters, constantly trimming your altitude to stay in a chosen band. All of that burns propellant or uses huge amounts of power. Turn the systems off, and the atmosphere starts to move you wherever the local flows want to take you, including down into higher pressure and more stress. Weather on Jupiter also isn't just wind and shear. The storms generate lightning that makes Earth's lightning look small. Observations from missions like Juno show flashes that are tens to hundreds of times more energetic than typical lightning strikes here. A single bolt can carry billions of joules of energy. That's enough to fry electronics, punch through thin hull sections, and induce massive currents in your wiring even if it doesn't score a direct hit. So your habitat needs serious lightning protection, not just a simple rod or two. You need thick conductive paths to guide currents safely, surge protection on every power line, shielding for data cables, and robust grounding systems, even though there is no ground, only an ocean of conducting gas. And lightning doesn't just dump energy where it hits, it also generates strong electromagnetic pulses. Those pulses can scramble sensors, glitch computers, and disrupt communications. Your entire control system has to be hardened in the same way we harden critical satellites, but for a much harsher environment. Even if you build all of that, you're still dealing with a fundamental difference between Earth and Jupiter, our storms end. Hurricanes on Earth form, rage, and then die out as they run out of warm water or hit land. Tornadoes last minutes to hours. You can fly above many storms, or sail away from the worst parts because there are calmer regions to reach. On Jupiter, there is no land to break the flow, no continents to disrupt circulation. Storm systems can wrap all the way around the planet, and giant vortices can persist for centuries. That means there is no quiet ocean to head into. The entire world is an ocean of gas, with jets, storms, and turbulence everywhere at different scales. You might find relatively milder zones, but not truly calm ones, and those zones can shift over time as global patterns change. A habitat cannot rely on the idea that if the weather gets bad, you just move a few hundred kilometers and wait it out. The next band over might be just as chaotic, and the sheer cost of moving around in this environment is huge. So when people talk about floating cities on Jupiter, the weather piece alone is enough to show how extreme that is. You're not hovering in a stable sky, you're fighting an atmosphere where your normal background wind is already in the range that destroys houses on Earth, where the signature storm is the size of a planet, and where lightning carries enough energy to cripple unprotected systems in an instant. And here's the problem that stacks on top of all of this. Even if you somehow survive the winds and the storms, the gas you're floating in is chemically wrong for you. It doesn't just starve you of oxygen, it actively attacks your hardware and your health, turning the whole atmosphere into a toxic, corrosive soup. You know how on Earth you can at least say, okay, the air might be polluted, but it's still air I can, in principle, breathe. On Jupiter, that basic assumption breaks instantly. The atmosphere is not just unbreathable, it is the wrong chemistry from top to bottom. Start with the simplest question, could you ever take your helmet off there? The answer is no, not even for 1 second. Jupiter's atmosphere is roughly 90% hydrogen and about 10% helium by volume, with small amounts of methane, ammonia, water vapor, and other trace compounds. There is essentially no free oxygen. Your lungs need oxygen molecules to pull into your blood, and here there just aren't any. You don't slowly suffocate, you get nothing useful from each breath. It's like trying to breathe pure fuel and balloon gas. Even if you tried to cheat and pump out pockets of normal air, a mix of nitrogen and oxygen like we have at sea level, that air wouldn't mix nicely with the surroundings. Hydrogen and helium are much lighter. Your breathable mix is heavier, so it behaves like a dense blob sinking through the lighter gas. Inside a habitat, that means your internal air is always trying to leak out and pool wherever gravity pulls it, while hydrogen is trying to seep in. Outside, if you vent air, it doesn't spread into the environment in a friendly way. It just falls like an invisible temporary cloud. Breathing directly from Jupiter's atmosphere is off the table, and even controlling air inside your structures becomes a constant balancing act. But let's say you keep the helmet on and accept that life is going to be 100% in sealed habitats and suits. You still have to deal with what those clouds you're flying through are actually made of. The colourful bands you see in telescope images aren't just pretty decoration, they're tied to real chemicals suspended in the gas. We think a lot of those clouds are ammonia ice, water ice, and possibly particles of ammonium hydrosulfide, a compound of ammonia and hydrogen sulfide. None of that is friendly. Ammonia is strongly caustic. It can burn eyes and lungs at relatively low concentrations, and it attacks many materials you might want to use in suits and seals. Hydrogen sulfide, the rotten egg gas, is toxic to humans in small doses. Ammonium hydrosulfide particles can break down and release that gas under some conditions, so any leak in your suit isn't just letting in harmless hydrogen, it's potentially bringing in a mix of irritants and poisons that damage your tissues very quickly. For electronics, these same chemicals are trouble. Fine cloud particles can settle on surfaces, dissolve tiny amounts of metals, and create conductive films where you don't want them. Moisture plus ammonia plus trace sulfur can make a corrosive cocktail that creeps into connectors and around insulation. You're basically operating your delicate gear inside a thin, planet-sized industrial chemical tank, with no way to ever shut it off or clean it out. So now think about your habitat or station sitting in that atmosphere for not just days but years. Even if you pick alloys that resist corrosion, long-term exposure to ammonia and related compounds slowly eats away at many metals. Surfaces get pitted, coatings blister and peel, protective paints degrade. Rubbers and plastics that are fine in vacuum or dry air can swell, crack, or dissolve when exposed to this gas mix. Every joint and seam on your station is a potential weak point. Corrosive molecules are tiny, they can diffuse into microscopic gaps and start breaking down adhesives and sealants long before you see visible damage. Over time, gaskets lose flexibility, O-rings stop sealing properly, cable insulation becomes brittle or soft in patches. You're already fighting pressure, temperature swings, and violent winds, and on top of that, the atmosphere itself is trying to crawl into every crack and slowly destroy the materials holding your life support together. Maintenance stops being occasional and becomes constant just to stay ahead of the damage. Maybe you say, alright, at least there's water up there, we know life loves water. Maybe that's a resource we can lean on. Yes, Jupiter does have water, but not in a way that helps you much. There's water vapor mixed into the gas, and there are probably water clouds in some layers, droplets and ice crystals riding the convective currents. What you don't have is a stable liquid ocean. No calm global sea where you can park a platform or drop intake pipes. Any liquid water that formed is part of the same wild churning system as everything else. It gets carried up and down, frozen, thawed and re-evaporated over and over. You can, in theory, collect water from the air, like industrial-scale dehumidifiers or condensers, but you're grabbing it grain by grain from a moving, hostile atmosphere. There's no equivalent of an Earth ocean where you lower a hose and pump. Every kilogram of water is a small engineering victory, not a free gift. And there's a final trap in this chemical soup that sounds like a benefit at first, but isn't. The fact that the main ingredient, hydrogen, is fantastic rocket fuel. It's tempting to think, hey, we're sitting in a giant ocean of fuel that has to make things easier. But fuel by itself is only half the story. To burn hydrogen in a rocket or power plant, you need an oxidizer, something like oxygen. Jupiter's atmosphere doesn't provide that. You have to import it or produce it using energy and resources from somewhere else. So you're not swimming in free fuel, you're surrounded by one ingredient that only becomes useful after you've put in a lot of effort and brought in other chemicals. Meanwhile, the same hydrogen and helium mix that looks good on a rocket spec sheet is a nightmare for containment. Hydrogen atoms are tiny, they diffuse through many materials, they embrittle metals, they leak through seals that would hold other gases just fine. Any tank or pipe you fill with hydrogen on Jupiter has to be designed not only to hold it under pressure, but to survive exposure to the external hydrogen environment and the corrosive trace chemicals at the same time. Every system that uses hydrogen, whether it's a fuel cell, a reactor, or a thermal machine, is running in an atmosphere that is already full of hydrogen and reactive compounds. A small leak doesn't just waste fuel, it mixes into a background where spark sources are everywhere, from lightning to static discharge. Safety margins have to be huge, and even then, the environment is doing you no favours. The thing that looks like your big advantage, endless fuel, actually adds another layer of risk and design complexity. So when you add it all up, Jupiter's atmosphere fails you on every chemical level. You can't breathe it, you can't ignore its toxicity, you can't trust it around your materials, and you can't even treat its main ingredient as a simple asset without solving new problems. And the really vicious part is, all of this chemical hostility sits on top of the mechanical chaos you already saw from the winds and storms. The gas isn't just poisonous and corrosive, it's also shaking you, slamming into you, and filling with lightning and turbulence that attack you on a smaller, more constant scale. Not just as rare giant events, but as micro-level killers that never stop. You've heard about the giant storms and jet streams, but the small-scale stuff on Jupiter is just as deadly. It's not only the big dramatic events that try to kill you, it's the constant background chaos that never gives your city or your ship a break. Even in the quiet bands between the big jets, the air is full of small emotions, little eddies, downdrafts, updrafts, pockets of rising and sinking gas. For a human habitat, that translates into continuous shaking. Not a rare jolt once in a while, but a constant low-level bumping and swaying. Think about the way a plane feels in bad turbulence. The little drops in your stomach, the random sideways nudges, the subtle vibration you can't quite escape. Now stretch that out, not for a 2-hour flight, but for every hour you are in Jupiter's atmosphere. Your structures feel that all the time. Floors are never perfectly still, walls are under small changing loads, support struts are always flexing a tiny bit one way, then a tiny bit the other way. That motion feeds straight into human bodies too. Your inner ear spends all day trying to recalculate which way is down. Some people would get motion sick, some would adapt, but everyone would feel tired faster because your brain is working overtime just to keep balance. Inside the city, everything that hangs, everything that is tall and thin is in motion. Cables sway, cranes sway, antennas sway. You can damp some of it with good engineering. You can add shock absorbers and stabilizers, but you can't remove the root cause. The gas around you is in constant small-scale motion. Over days and weeks, those small motions turn into real stress on the frame. Now that's if you're just trying to float with the flow. As soon as you try to move fast through the pit's layered atmosphere, another problem appears: shockwaves. If your craft is moving at high speed relative to the local gas, especially if it's approaching or passing the speed of sound in that region, the air can't get out of the way smoothly. It piles up in front of your hull and forms a shock front. At that shock front, pressure and temperature jump sharply. The leading surfaces of your vehicle see sudden spikes in heating and force. On Earth, we mostly worry about this high up, when spacecraft are re-entering through thin air. On Jupiter, the air gets thick much higher up, and the winds are already fast, so you hit conditions that feel like hypersonic re-entry at altitudes where, on Earth, you'd still be in relatively gentle flight. That means your heat shields, your leading edges, and your sensor windows have to be built for extreme loads much earlier in the descent or maneuver. If you misjudge the local wind and push your craft too hard, you can create shockwaves strong enough to damage your own structure, even if you're not technically re-entering in the way we usually mean. Every fast move becomes a calculation because the atmosphere is ready to punish any aggressive profile. On top of this mechanical beating, the electrical environment is nasty. Every lightning strike on Jupiter is not just a flash of light, it's a huge burst of radio energy. And you're living in a place where lightning is frequent and powerful. Add to that the radio noise from Jupiter's own magnetosphere, and you get an environment that is loud across a wide range of radio frequencies, from kilohertz up into tens of megahertz and beyond. Your communication systems, your navigation beacons, your radar, all of it has to work inside what is basically a planet-sized radio jammer. Signals from your own equipment are fighting through a storm of natural interference. You need strong error correction, redundant channels, maybe laser links just to keep stable connections between different parts of your own city. Any long-range talk to orbiting stations or passing ships has to punch through layers of static and sudden spikes when a lightning cluster goes off nearby. Electromagnetic pulses from nearby strikes can induce currents directly in your wiring and structures. That means random voltage surges hitting control electronics, sensors, and even life support systems. On Earth, we design for occasional lightning, with surge protectors and grounding rods. On Jupiter, you'd have to assume lightning is a regular part of your operating environment. Shielding gets thicker, circuits get more complex, and you still accept that some fraction of your gear will glitch or die early. All of this motion and shock doesn't just make the moment-to-moment experience rough, it wears your city down over time. Continuous vibration slowly loosens bolts and fittings. Even small shaking cycles, repeated millions of times, cause metal to fatigue. Microscopic cracks start near welds and sharp corners, then grow. Composites, like carbon fiber materials, can delaminate layer by layer. Seals that were perfect in the lab start to leak a tiny bit as surfaces move and reshape under stress. Every lightning hit, every gust, every little pressure spike adds another tiny contribution to that damage. Over months and years, the design lifetime of your components shrinks. Parts that might last decades in orbit around Earth might last only a fraction of that time here, because they are never at rest, never in a clean, quiet, stable environment. And remember, just inspecting and repairing that damage is hard. To get to the outside surfaces, crews have to go out in suits into fast winds, corrosive clouds, and strong radiation. Drones can help, but they face the same turbulence and electrical noise. You don't get to roll your city into a dry dock and give it a full overhaul. It is always flying, always loaded, always under attack from the microscale chaos. So even before you talk about the big stuff like massive radiation belts and giant magnetic fields, Jupiter is already grinding your technology down from the inside out and the outside in. The environment shakes you, shocks you, and scrambles your signals in a million tiny ways every single minute. And the brutal twist is, all of that is happening inside a magnetosphere that's far larger than the planet itself. a magnetic bubble loaded with high-energy particles that turns the space around Jupiter into something closer to a particle accelerator than a safe orbit. You've seen how the small-scale chaos around Jupiter shakes a city apart, but all of that is happening inside something even worse. A magnetic field so big and so aggressive that space around the planet behaves more like the inside of a particle accelerator than empty vacuum. Jupiter's magnetic field doesn't just sit close to the clouds, it inflates a magnetosphere that stretches roughly 7 million kilometers toward the Sun. And on the night side, it reaches out almost as far as Saturn's orbit. If your eyes could see radio and charged particles, Jupiter's magnetic bubble would look larger on our sky than the full moon, even though it's nearly 1,700 times farther away than the moon is from Earth. On Earth, you can think of the magnetic field as a shield that helps deflect charged particles. Around Jupiter, shield is the wrong word. The magnetosphere traps particles instead of letting them go. Solar wind electrons and ions, plus material from the moons, get caught and spiral around the field lines. They bounce back and forth between north and south magnetic poles, they drift around the planet, and they don't escape easily. Over time, that builds up dense belts of high-energy particles, effectively turning space near Jupiter into a radiation minefield. The system doesn't just sit there passively, it's constantly being refilled, and one moon in particular is responsible for dumping new material into it non-stop. Io is covered in active volcanoes that erupt sulfur dioxide gas into space. That gas doesn't stay neutral for long. Ultraviolet light from the sun and collisions with existing particles strip electrons off those molecules, ionizing them. Now they're charged, so Jupiter's magnetic field grabs them. The result is a donut-shaped cloud, a plasma torus, of ionized sulfur and oxygen wrapped around Jupiter along Io's orbit. Estimates put the rate at roughly 1,000 kilograms of new plasma every second being added to the system. The rotating magnetic field drags that plasma along, forcing it to correlate with the planet's rapid 10-hour spin. That means heavy ions and electrons are being whipped around at enormous speeds, slamming into any object that strays into the region, including spacecraft and, in your scenario, any stationary ship trying to operate nearby. Those trapped particles don't just move in circles, they spiral along the magnetic field lines. And when charged particles spiral like that, they emit electromagnetic radiation. In this case, a lot of it is in the radio range, so Jupiter behaves like a natural synchrotron, a kind of particle machine that accelerates electrons and makes them radiate. In some ways, it's even a bit like a weak radio pulsar, beaming out radio noise as particles zip around and crash into the atmosphere near the poles. On Earth, auroras are a beautiful side effect of this kind of process. Charged particles spiral down our field lines and hit the upper atmosphere, making atoms glow. On Jupiter, that same basic physics is cranked up to extreme levels. Auroras there pump out energy in infrared, ultraviolet, and even X-rays. These are fantastic for astronomers because they tell us a lot about the magnetic field and the particles inside it. But for your electronics, your sensors, and your crew, it's a constant reminder that you're sitting inside an active radiation machine. Your communication gear now has to operate in a place where background radio noise is high across a broad range of frequencies. Those synchrotron emissions and radio bursts from lightning aren't gentle static, they are strong structured signals that can drown out your own transmissions. Antennas pick up Jupiter's emissions whether you want them to or not. You can switch to higher frequencies, use tight beams and heavy error correction, but nothing makes the magnetosphere quiet. Navigation systems that rely on faint signals, like distant beacons or pulsar timing, have to work harder to separate the useful signal from the loud background. There's another layer to this, and it's easy to miss: the electric currents that move through this whole system. The interaction between Jupiter's magnetic field and its moons, especially Io, sets up huge current circuits. Plasma flows along magnetic field lines between the moon and the planet, closing loops through the ionosphere and magnetosphere. These are not tiny lab currents, they are measured in millions of amperes. When those currents dump energy into the upper atmosphere, they heat it, drive auroras, and help maintain the radiation belts. For a human habitat, that means you're inside a plasma environment where large currents and changing magnetic fields are normal. Conductive structures in your ships and stations can have currents induced in them just by moving through the field or by changes in the surrounding plasma. That can cause unexpected voltages, heating, and electromagnetic forces on cables, frames, and hulls. You'd have to design your station almost like a piece of power grid hardware dropped into a storm, with careful control of grounding paths, isolation between critical systems, and constant monitoring of induced current levels. Big loops of metal in your structure can act like unwanted antennas and generator coils, turning magnetic field changes directly into power spikes. If you ignore that, you risk parts of your structure literally feeling mechanical forces from the currents, or electronics being stressed by surges that came from the environment, not from your own power plants. The magnetosphere also affects where you can safely park anything in orbit. Low orbits close to Jupiter's cloud tops dive right into the intense inner radiation regions. Higher up, you might find slightly safer pockets, but you're still inside a giant magnetic trap. Every choice of altitude trades off radiation dose against operational convenience. And because Jupiter's magnetic field is tilted relative to its rotation and offset from the planet's center, the radiation environment is not perfectly symmetric. That adds complexity to planning stable, predictable orbits for stations and transfer vehicles. All of this means that even before you count the radiation dose to human tissue, the magnetic environment alone is a major engineering challenge. It makes communication harder, it makes power management harder, it introduces new mechanical forces, and it fills space with high-energy particles that constantly slam into your hardware. You're not just orbiting a big planet, you're operating inside a magnetic machine that's actively accelerating particles and throwing them at you from multiple directions. And the part that turns this from difficult into almost impossible for humans is what those particles actually do when they hit you. The magnetosphere shapes and feeds Jupiter's radiation belts, regions where charged particles reach energies high enough to damage cells in minutes. If you try to live anywhere near Jupiter long term, you're effectively trying to build a town inside the spill zone of a giant natural nuclear reactor. And that's where the next problem comes in, the raw radiation field itself. You've seen how Jupiter's magnetic field traps charged particles. Now you have to look at what that actually means for a human body, because here, the numbers stop being uncomfortable and jump straight to deadly in minutes. Around Earth, you live inside the Van Allen belts, but they're small and relatively weak. Around Jupiter, the whole radiation bubble is on a different scale. Studies for missions like Europa Clipper put Jupiter's particle radiation field at about 20,000 times larger in volume than Earth's, and roughly 1,000 times stronger than Saturn's. That's not a small upgrade, that's a completely different environment. In practical terms, doses that would take months or years to accumulate around Earth can hit you in minutes or hours near Jupiter. High-energy electrons and ions slam into your body and your equipment from every direction. They strip the electrons off atoms, break DNA strands, and create cascades of secondary particles inside your tissues. You don't feel it directly, there's no tingling, but your cells are being physically damaged, right down at the molecular level every second you stay exposed. You might think, fine, I won't go close to the planet, I'll live out at the moons, that has to be safer. But the numbers out there are still brutal. Radiation dose is often measured in REM, which is a unit that roughly tracks biological impact. A few hundred REM as a whole body dose delivered over a short time can be fatal for humans. Near Io's orbit, estimates are around 3,600 REM per day. At Europa, it's still roughly 540 REM per day. So just standing at Io's orbital distance, unshielded, you could take a lethal whole-body dose in well under an hour. Even at Europa, you're in the range where a single day's exposure unprotected would be enough to cause severe radiation sickness and a very high chance of death later from organ damage or cancer. And remember, these are at the moons. Closer in, inside the main belts near Jupiter itself, the environment is even harsher. We already have real hardware experience that shows how bad this is, and that's just for electronics. Probes like Pioneer, Galileo, and Juno all needed heavy shielding around their sensitive components. Even with that, their mission plans had to account for cumulative radiation damage. Pioneer 10's passage through Jupiter's belts gave it an integrated dose measured in hundreds of thousands of rads, far, far beyond anything a human could survive. Juno flies on elongated orbits that dive in and then swing back out, partly to limit how long it stays in the worst of the belts each time. Even so, these spacecraft experience glitches, sensor noise, and occasional failures caused by high-energy particles flipping bits in memory or outright damaging circuits. You see single-event upsets, where one particle hits a chip and changes a digital 0 to a 1. You see degraded solar panels and detectors over time. Now imagine replacing electronics with organs and cells. The same kind of particle hits that ruin a chip are breaking DNA, killing stem cells and damaging bone marrow. Shielding that is just barely enough for a probe still leaves a human completely unprotected. So can you fix this with enough armour? Just wrap your city in a thick shell and hide inside. On the International Space Station in low Earth orbit, a few centimetres of aluminum plus water and other materials in the station walls are enough to keep radiation at levels that are high but manageable. Around Jupiter, that kind of shielding is nowhere near enough. To bring exposure down to something similar, you'd be looking at meters of dense material. That's more like burying your habitat inside a small asteroid, not just bolting on a few extra plates. You'd want layers of rock, regolith, or thick water tanks around all living spaces. Every meter of shielding adds mass, and mass is the enemy of rockets. To get that much material off Earth, accelerate it out to Jupiter, and then support it in an environment where gravity at the 1 bar level is about 2.5 times stronger than on Earth is a huge challenge. A habitat that weighs 1,000 tons on Earth suddenly feels like 2,500 tons in Jupiter's gravity. So your radiation-safe Jupiter city isn't a sleek floating station, it's a massive bunker, a lead or rock mountain that you somehow have to keep intact, structurally strong and held at a fixed altitude inside a high-speed, corrosive, storm-filled atmosphere. Every extra meter of shielding makes the structure stronger against radiation, but harder to keep afloat and harder to move. The more you protect yourself from particles, the harder gravity and weather hit you. You can try to cheat by living much farther out, beyond most of the belts, maybe in high orbit or out by the calmer moons like Callisto, where doses are lower. That's exactly why mission planners like those outer moons. They sit in pockets where the radiation is comparatively mild. But then you're not living at Jupiter anymore. You're living near it, using it as a backdrop or a gravitational anchor. The planet itself remains in practice off limits to human bodies, except for very brief, very risky passes in heavily shielded craft. And here's the climax of this piece. Even if you built that insane shielded bunker, even if you had the mass to block most of the radiation, and you somehow kept it floating against 2.5 G in screaming winds, you still haven't solved the problem of getting people in and out. Because the only way to reach any layer of Jupiter's atmosphere is to drop into that gravity well and then try to climb back out, and that descent and ascent happen through the same thick gas that crushes probes and produces re-entry conditions far worse than anything we've handled so far. The radiation tells you not to stay, and the descent profile makes sure that leaving is just as deadly as living there. When you talk about going to Jupiter, you're really talking about falling into Jupiter, and that fall is where the planet finishes the job. The way down isn't a landing, it's a controlled crash that only ends because your hardware gives up before the atmosphere does. Start with the one time we actually tried this for real. The Galileo entry probe hit Jupiter's upper atmosphere at more than 47 kilometers per second, over 100,000 miles per hour. That's not a gentle arrival, that's a bullet. As it ploughed into the gas, it slammed into a wall of drag, and the deceleration spiked to something like 230 G. That means the probe effectively felt a force 230 times stronger than its own weight on Earth. No human can survive that. Even with perfect restraints, blood, organs, bones, everything would be crushed. We only survived it on the engineering side by making the probe unmanned, compact and sacrifices built in. A thick heat shield took most of the punishment. The probe rode the fire, slowed down, jettisoned the burned shield, deployed a parachute and started sending back data. From that point, it lasted less than an hour. In that short time, it dropped from near zero pressure to roughly 22 bars, about what you'd feel at 200 to 300 meters, 600 to 900 feet under Earth's oceans. Temperatures climbed from near space cold up to about 150 degrees Celsius, around 300 degrees Fahrenheit. Then the signal stopped. The environment simply pushed beyond what the probe was rated for, and it died. That was the best case, a one-way robotic dive, with no plan to come back up. So what happens if you try to make that descent human-rated? On Earth, re-entry is hard, but the basic idea is clear. You come in at high speed, hit a relatively thin layer of air, let drag slow you down while a heat shield handles the fire. Then once you're slow enough, you pop out parachutes and glide or drop onto solid ground. There's a peak heating period, then things calm down and there's a clear endpoint, the surface. On Jupiter, that pattern breaks. There is no ground. The atmosphere just keeps getting thicker and hotter as you go down. If you try to use aerobraking the way we do around Earth, you run into a problem. Where do you stop? You can't just cut speed, deploy chutes and flare for landing. The chutes pull you through more and more dense air with more and more drag. Gravity is stronger, about 2.5 times Earth is near the 1 bar level, so you're still being pulled down hard while the atmosphere fights your vehicle from all sides. If you say, fine, I won't rely on drag, I'll descend slowly on propulsion, you get hit from the other side. Thrust has to fight Jupiter's gravity 24/7 just to keep your vertical speed under control. That means burning huge amounts of fuel continuously. While you're doing that, you're still flying through high winds, turbulence, and shock heating from relative motion. You're using engines at full power in the middle of a storm world with no safe coast phase where you can relax. Re-entry systems in our current playbook are designed around a simple assumption. There's a finite window of high heating. You speed up, you hit the air, things get insanely hot for a short period. Your heat shield ablates, carrying heat away as it chars and vaporizes. Then you slow enough that the heating drops off. After that, the atmosphere cools your vehicle rather than cooking it. On Jupiter, the deeper you go, the hotter the surrounding gas gets. Even if your descent speed is under control, the ambient temperature keeps climbing. That means the heat load can keep going up instead of peaking and falling. Your shield is not just dealing with friction heat, it's dealing with hot gas pressing on it from all sides. Ablative material burns away, underlying structure heats, and at some point the core materials soften. Metals lose strength at high temperature, composites start to break down, seals fail. You don't get a clean through the fire and out the other side phase, you just move from one mode of overheating to another until something gives. Mechanically, the story is similar. Loads from drag, turbulence, and pressure don't drop to zero when you reach some imaginary runway. They keep increasing as you head into denser layers. Your frame is under compression from outside pressure, tension and bending from wind and maneuvers, and intermittent shocks from gusts and shear. A design that could survive Earth re-entry several times might last once, maybe less, in a deep dive on Jupiter. Now ask the next question. Suppose you somehow build a robotic probe that can go deeper than Galileo, maybe with better materials, better cooling, and a tougher pressure vessel. Does that get you any closer to a human mission? The answer is basically no, because surviving the fall is only half of a normal mission profile. You normally also plan a way back out. On Jupiter, that second half is where everything collapses. To leave Jupiter's gravity from the cloud tops, you need close to 60 kilometers per second of speed, over 130,000 miles per hour. That's more than 5 times Earth's escape speed. From deeper in the atmosphere, it's even worse because you have to fight through thick gas as well as climb the gravity well. There is no realistic ascent stage we can design today that sits deep in that soup, lights its engines, claws through crushing pressure and drag, and then accelerates to escape speed. Any engine powerful enough to do that would be dealing with hotter, denser air than any rocket has faced. Exhaust would mix with the surrounding gas in violent ways, Vehicle control would be incredibly hard and the structure would already be weakened from the descent. Even if you put nuclear or futuristic propulsion on the table, you're still asking that system to work inside a hot, high-pressure, chemically hostile environment, not in a clean vacuum. So when you talk about sending humans down into Jupiter's atmosphere, you are in practice talking about a one-way trip. There is no business case, no rescue plan, no credible architecture that lets you take people down and bring them back up again. Every factor you've seen piles on: the pressure, the temperature, the gravity, the winds, the radiation. All of it lines up to make descent the final chapter, not the middle of a round trip. And here's the twist that keeps the tension rising. All of this horror assumes you've already solved another huge problem, just getting a crew to Jupiter in the first place. Before you even start a dive, you have to cross a deep stretch of the interplanetary space, spend months to years in transit, and run a supply chain into a gravity well that wants to keep everything it catches. The journey to Jupiter on its own is already harsh, and when you add that to an environment that turns any landing into a death sentence, the idea of living on Jupiter stops being ambitious. How bad is Jupiter if it's already fighting you before you even get close to the clouds, just out in space on the way there? The distance and time alone make it clear this is not somewhere you casually commute to from Earth and back. Start with where Jupiter actually is. It orbits the Sun at about 5.2 astronomical units, so more than 5 times farther out than Earth. Light spreads out as it travels, so by the time sunlight reaches Jupiter, it's only about 1/25 as bright as it is here. That means solar panels that work well near Earth suddenly drop to around 4% of their output. A solar array that gives you, say, 100 kilowatts near Earth might barely deliver 4 kilowatts at Jupiter for the same area. So for serious power, you can't rely on sunlight in the same way. You lean heavily on nuclear power or other very high-density sources. That adds weight, complexity, and safety issues. Any ship or station you send has to carry reactors, shielding for those reactors, and robust cooling systems in an environment that's cold, dark, and far from home. You can still use solar for small tasks, but the era of big solar farms powering a city doesn't work well that far out. The basic energy budget is worse before you even start dealing with the planet's own violence. Now think about how long it takes just to get there, with propulsion we actually know how to build. Using efficient trajectories with gravity assists, you're looking at something like more than a year of travel time for a crewed mission, potentially longer depending on the exact path and launch window. This is not like a few days to the moon or a few months to Mars. This is a long haul across deep space. For that entire time, your crew is exposed to cosmic rays and solar radiation, only partially shielded by the hull. They're in microgravity or partial gravity, losing muscle and bone unless you add complex artificial gravity systems. Life support has to keep recycling air and water with almost perfect reliability, because resupply is not an option once you're on the way. Every gram of food, spare parts and medicine has to be loaded before departure or manufactured en route. Micrometeoroids are also a real threat. A small piece of rock at tens of kilometers per second can punch a serious hole in a ship. And all of this effort is just to arrive near a planet that we already know is lethal if you treat it like a potential home. You're spending more than a year in a dangerous transit, burning fuel, stressing hardware, exposing humans to radiation and zero-G, just to pull up next to an object that has no surface, extreme gravity, crushing pressure, and deadly radiation belts. The cost-benefit balance is already skewed heavily in the wrong direction. Communication also becomes a very different game at Jupiter distances. Radio signals travel at the speed of light, but the space between Earth and Jupiter is huge. Depending on where the two planets are in their orbits, a radio message can take from about 15 to 25 minutes one way, which means something like 30 to 50 minutes for a round trip. That delay kills real-time control. You can't have mission control on Earth, flying your landers like drones, reacting instantly to problems. If something goes wrong in a descent or a storm, by the time your help message arrives at Earth, the emergency has already played out. Any response that comes back is late by definition. So crews near Jupiter must be highly autonomous, with local decision-making and local problem-solving. You can't lean on the usual human habit of we'll figure it out from home as we go. If your system design or your procedures have serious flaws, you will discover them in real time, with almost no chance for fast outside help. Now stretch that communications problem to routine operations, software updates, new procedures, medical advice, all of them have that same lag. A simple back and forth conversation that takes 2 minutes on Earth might stretch to an hour or more. The psychological strain on crews increases. They're not just physically far away, they're also isolated by time, and that makes every serious decision heavier. Then there's the logistics side, the supply chain into a gravity pit. Every kilogram of stuff you want at Jupiter, food, tools, replacement parts, shielding, extra propellant, has to be lifted up from Earth or mined somewhere else first. Lifting from Earth means launching into orbit, which is already expensive. Then you accelerate that cargo out to Jupiter, which needs more energy than going to Mars. And once you arrive, if you actually want to get close to the planet rather than just orbiting far out, you have to drop down into that deep gravity well. It's like delivering cargo to the bottom of a very deep mine shaft, where the elevator ride down is expensive and dangerous, and the elevator ride back up is even worse. Compared to this, sending supplies to low Earth orbit or the Moon looks cheap and easy. Even Mars, with all its problems, is a much shallower, closer target in pure energy and time terms. Jupiter is on the opposite end, far away, dark, and sitting behind a large barrier of delta, the speed change you need to get in and out. And because that gravity well is so deep, you can't easily build a self-sufficient economy at the bottom that pays you back. On the Moon or Mars, in theory, you can dig up resources and slowly reduce how much you need from Earth. On or near Jupiter, particularly if you're anywhere close to the atmosphere, the environment is so hostile that almost everything you do costs huge amounts of energy and engineering effort. The idea of a colony that starts small and grows into a self-running settlement makes sense in some places. Near Jupiter, it looks more like building a remote outpost that permanently depends on an incredibly expensive slow supply line. So just on distance and time, before you combine in pressure, temperature, and radiation, Jupiter fails a basic test for human settlement. It's far, it's dark, it's slow to reach, communication is laggy, and the cost of delivering mass into its gravity well is enormous. And yet, even with all those warnings, people still like to say, okay, we won't land, we'll just float, we'll build cloud cities in the upper atmosphere where things are gentle. But once you stack everything you've seen, gravity, pressure, temperature, storms, chemistry, radiation, and logistics, on top of that floating city idea, you see that even the most optimistic version of a Jupiter sky habitat collapses under its own weight. The nice pressure layer idea sounds good on paper, right? You pick an altitude where the pressure is about 1 bar like sea level on Earth, and maybe the temperature is only brutally cold instead of totally insane, then you float a city there. People compare it to the Venus aerostat concept and say, we'll just do that, but in Jupiter's atmosphere. The problem is, once you look at the actual physics, the whole cloud city concept falls apart piece by piece. Start with the basic pitch. You choose a layer where the pressure is manageable, around 1 bar or maybe a few bars. You fill big envelopes with a lighter gas, helium or hot hydrogen, and you let buoyancy do the work. The outside atmosphere is hydrogen rich. Your inside gas is a little less dense, so you get lift. In this picture, you don't need rockets firing all the time. You mostly just float and use small thrusters to steer. That's the clean, simple version people like to sketch. Now look at the first real problem, buoyancy and hydrogen. On Earth, air is mostly nitrogen and oxygen, which are relatively heavy molecules. If you fill a balloon with hydrogen, which is the lightest common gas, you get a big density difference, so you get strong lift. That's why hydrogen and helium balloons work here. On Jupiter, the background gas is already mostly hydrogen with some helium mixed in. You're trying to float in the lightest stuff nature normally gives you. If you fill your balloon with helium, which is a bit lighter than hydrogen for a given pressure and temperature, you get only a small improvement. If you heat hydrogen inside the envelope so it's warmer than the outside, you expand it and make it slightly less dense, so you get some lift that way too. But in both cases, the difference in density between the inside and outside gas is tiny. That means for every ton of mass you want to lift, you need a huge volume of balloon. Add Jupiter's gravity to that. At the 1 bar level, gravity is about 2.5 g, so every kilogram of structure, equipment, shielding and people weighs like 2.5 kilograms. Your envelopes have to support not just the mass, but that mass multiplied by 2.5. The lift per cubic meter is small, the effective weight per kilogram is high, and you're trying to balance those two with a system that must not tear, leak or collapse. You don't end up with a compact floating city, you end up with incredibly large, fragile envelope systems just to hold up a relatively modest payload. Even if you somehow solve the lift problem and get a platform that can float at a chosen pressure level, the next issue is staying where you want to be in an atmosphere that refuses to sit still. Jupiter's jet streams are strong, with wind speeds in many bands reaching hundreds of kilometers per hour, hundreds of miles per hour. Those flows aren't uniform with height or latitude, so your city is always being pushed and twisted. On a planet with ground, you could drop tethers and anchor your platforms to rock or ice. Here, there is nothing to tie to. Any anchor line just hangs in the gas, adding drag and stress without giving you a fixed reference point. So you're left with one option: active control. That means using thrusters, control surfaces, or some other propulsion to fight the wind and hold position, or at least keep a stable orientation. Running engines constantly in a dense, fast-moving, corrosive atmosphere is not a side detail. It becomes the baseline. You burn propellant non-stop, or you dump huge amounts of electrical power into some advanced propulsion system just to avoid drifting into more dangerous regions or descending into higher pressure. If you ever lose power for long, the atmosphere takes over and pushes your city wherever the local flows are going, including down into layers with more pressure and more heat. Some people try to dodge another problem by saying, okay, we'll float high, above the worst of the radiation. But the radiation belts around Jupiter don't sit inside the clouds, they extend far above them. Being at the 1 bar level doesn't automatically put you in a safe zone. You can pick latitudes and altitudes where the radiation is lower than in the most intense parts of the belts, but lower here still means much worse than anything in low Earth orbit. So your cloud city still needs heavy radiation shielding, thick layers of water, polyethylene, or rock-like materials around living areas. That adds even more mass, which reduces buoyancy margins further, which forces even bigger envelopes and stronger structural frames, all in 2.5 g. You're in a constant trade-off. Do you add more shielding and struggle to stay afloat, or add less shielding and cook your crew slowly with radiation? There's no easy pick. Then you get to maintenance and repair, which is where the whole fantasy really starts to look like a non-stop emergency drill. All the systems that let your city float and stay alive sit out in the environment you've already seen is awful. Thrusters and control surfaces are in fast, turbulent winds, balloon skins are hit with ammonia and other corrosive chemicals, plus temperature swings and constant flexing. Antennas and sensor masts get battered by turbulence and hit by lightning. Radiators are working in air that is sometimes freezing, sometimes warmer, sometimes full of charged particles. Every one of those external systems will fail over time. Seams on the balloon envelopes will develop leaks. Thruster nozzles will erode. Joints will wear out. Protective coatings will peel. To fix any of it, you have to send crews outside in suits, or rely on drones that have to contend with the same wind, chemistry, and radiation. There's no calm weather window, no quiet season. You're always working in high winds, with the platform shaking in air that's trying to corrode your suit and zap your electronics. So daily life in this city looks less like a futuristic, peaceful cloud habitat, and more like continuous crisis response. Teams patching holes, swapping parts, dealing with electrical faults, and racing the clock on corrosion and fatigue. The margin for error is tiny. A big leak in an envelope, a serious thruster failure, or a major lightning strike in the wrong place can quickly cascade into loss of buoyancy or loss of control. In other words, the whole structure starts sinking or tumbling, and there is no ground underneath to catch you, just denser gas, higher pressure, and higher temperatures. And remember, even if you somehow made a cloud city that floats, holds position, and keeps its people alive against weather, chemistry and radiation, the planet underneath is still not giving you any help. The gravity is still strong, the atmosphere still has no bottom, and just above your head, space is filled with a magnetosphere that pulls in high-energy particles. You're hanging in a narrow, violent band between a crushing interior and a radiation-soaked outer space. The more you try to scale this city up, the more you run into a last set of problems that people usually only talk about in sci-fi, the way gravity itself varies across big structures. Near a gigantic planet like Jupiter, gravity isn't perfectly uniform. It changes with depth and distance, and that gradient means the top of a huge habitat can feel slightly different gravity than the bottom. Take that, mix it with tidal forces and orbits very close to a massive world, and the next threat appears. Large-scale structures being pulled and flexed by gravity itself, not just by weather. All the problems so far assumed gravity was just one fixed number pulling straight down on you. But near Jupiter, even that isn't stable. The gravity itself changes from place to place, and that shift quietly pulls your structures apart over time. Start with what happens as you move up and down near the planet. Because of how Jupiter's mass is spread out inside, gravity doesn't just smoothly drop as you go inward, the way it would in a simple textbook sphere. From the cloud tops, if you go down a bit, the gravitational pull actually increases before it eventually falls off deeper inside. That means there's a gradient, a change in the strength of gravity with depth, even across relatively small vertical distances. For a person, that difference over a few meters is tiny. You won't feel your feet being pulled harder than your head in any obvious way. But for a big structure, like a tall floating habitat or a long tether system, the bottom of the structure sits at a slightly stronger gravity than the top. That creates differential forces. The lower parts are pulled down just a bit harder than the upper parts. The result is a constant, gentle stretch along the length of the structure. Now combine that with everything else you already have. The shaking from turbulence, the stress from winds, the weight of your own shielding in 2.5G. The gravity gradient adds another direction of stress, always on, always trying to pull long elements a little tighter. Over time, that means more fatigue in beams, more tension in cables, more load on joints that connect top modules to bottom modules. You can design for it, but you don't get to ignore it. It's one more thing that's trying to unbuild what you built. If you decide to avoid the atmosphere completely and live in a low orbit just above the cloud tops instead, Jupiter still hits you with gravity in another way, tidal forces. Tides are just the difference in gravity from one side of an object to the other. Jupiter's mass is so large that even across a station only a few kilometers long, the gravity on the side closer to the planet is meaningfully stronger than on the far side. That difference tries to stretch your station along the line pointing toward Jupiter, while compressing it in directions at right angles. The entire structure is being flexed by this tidal pattern on every orbit. It's the same basic effect that can tear apart weak comets that get too close, just scaled to whatever you put near the planet. Your station doesn't rip instantly, but every orbit puts a mechanical cycle into your frame, like bending a metal strip back and forth. Enough cycles and cracks develop, so a low-orbit platform has to be built like a giant unified piece, not a loose collection of modules with flexible links. All the joints and trusses need to be strong enough to take that repeated stretching and squeezing without loosening or failing. And remember, you're not in clean vacuum here either. The inner orbits near Jupiter also sit inside serious radiation belts. So the same beams and cables carrying tidal loads are also being slowly weakened by radiation damage and by charged particles burrowing into materials over time. If you get ambitious and try to put something even bigger close in, like a huge rotating ring station, you run straight into Roche limit issues. The Roche limit is the distance inside which a body held together only by its own gravity can be pulled apart by tidal forces. Your station isn't held together by gravity, it's held together by materials and engineering, so you're not as fragile as a rubble pile comet. But the same idea still matters. The closer you go to Jupiter, the stronger those tidal forces become relative to the strength of your structure. A loosely bound megastructure, like a big ring made of segments linked by hinges or flexible joints, starts to feel those tides as real separation forces. The part closer to Jupiter wants to orbit a bit faster, the farther part a bit slower. If your connecting structures can't keep them in sync, the ring tries to pull itself apart. You can compensate with active control, clamps and high-strength materials, but your safety margins shrink the lower you go. Design that is safe in a high orbit might be marginal just a few thousand kilometers closer. Radiation makes this worse. High-energy particles can change the properties of materials. Plastics become brittle, some metals can suffer from embrittlement or subtle structural changes, and electronic control systems that run your active stabilization are taking damage over time. So the very systems you rely on to keep a big ring or platform in one piece are themselves being worn down by the same environment you're trying to resist. Sci-fi loves the idea of gigantic ring habitats hugging a big planet, giving you stunning views of swirling clouds below. Around Jupiter, that picture is fighting not just tiny microgravity jitters or orbital drift, but serious large-scale stresses from gravity gradients and tides. Every segment of the structure has slightly different orbital tendencies, different gravitational pulls and different radiation exposure. The ring is constantly being twisted, stretched and bombarded. Long-term structural integrity under those conditions becomes a major unsolved problem. You need materials that stay strong under constant mechanical cycling, high radiation and temperature variations. You need joints that don't loosen even after millions of small flexes. You need monitoring systems that can spot hairline cracks or subtle warping before they grow into failures. And you need redundancy everywhere, because a single broken support in the wrong place could trigger a chain reaction of failures as loads shift suddenly to neighbouring sections. For smaller stations, you can beef up everything, keep the design compact, and accept limited lifetimes before you deorbit or retire the structure. For truly massive megastructures, the kind that would house big populations and industries, the numbers become ugly. The mass you need to ensure safety skyrockets, the repair demands go way up, and the consequences of any major failure are catastrophic, with pieces of the structure either falling into the atmosphere or becoming dangerous debris fields in orbit. So gravity near Jupiter isn't just strong, it's uneven in ways that hurt you, changing with depth, pulling harder on closer parts of your city or station than on the far parts, forcing your designs to be more rigid, more reinforced, and more actively controlled than similar structures would need to be around smaller worlds. And after all of that, you still haven't touched the biggest scale question. Even if you could handle the gravity, the tides, the radiation, the storms and the distance, does it ever make sense to try to reshape Jupiter itself or seriously live in its atmosphere, instead of going for the far easier targets right next door, its moons? When people ask, why don't we just terraform Jupiter, they're basically asking, why don't we rebuild a star by hand? The scale is that far off from anything you normally mean by planetary engineering. Jupiter has more than twice the mass of all the other planets in the solar system combined. It's mostly hydrogen and helium, the same basic stuff stars are made of. To make it Earth-like, you'd have to do several impossible things at once. You'd need to strip away a huge fraction of that gas so the gravity isn't crushing and the pressure at depth is manageable. You'd have to change the overall composition so the atmosphere isn't 90% hydrogen with almost no oxygen. You'd have to somehow flatten the pressure and temperature profiles so you get a real surface, or at least a stable shell, instead of an endless gradient from thin gas to metallic fluid. On top of that, you'd need to tame the magnetosphere and radiation belts, which are powered by Jupiter's rotation, internal structure, and interaction with its moons. That means changing how fast it spins, how its interior moves, maybe even altering its internal heat flow. At that point, you're not doing terraforming in the usual sense, like thickening Mars's atmosphere or adjusting Venus's clouds. You're trying to undo the basic physics of a gas giant. It's closer to stellar engineering than planetary engineering. The energy, time, and matter you'd need make it a fantasy, not a project. So if turning Jupiter into a comfortable world is off the table, what about using it as a resource instead? Especially all that hydrogen and helium. In theory, it's a huge reservoir of propellant. In a distant future, you could imagine robotic tankers dipping into the upper atmosphere, skimming hydrogen, compressing it, and hauling it back up to orbit to feed fusion reactors or high-efficiency rockets. That uses Jupiter as a fuel depot without asking it to be a home. But once you talk about putting people into that operation, the analogy gets ugly. You're dropping crewed vehicles into an atmosphere with hurricane-level winds as normal, exposed to lightning, turbulence, corrosive chemistry, and strong gravity. That's like sending divers, without automation, into the centre of a major storm at sea to scoop up buckets of water. It makes far more sense to keep humans well away from that environment and let machines do the dangerous part. Robots don't care about G-forces the way you do. They don't get cancer from radiation, and they can be designed to accept a limited lifetime in brutal conditions. So if Jupiter itself is not going to be living space but might one day be a fuel and energy source, where do humans actually go if they want to live in the Jupiter system? The obvious answer is the moons. Big ones like Ganymede and Callisto, and carefully chosen spots on Europa if you're willing to invest in serious radiation shielding. These bodies are solid, they have actual surfaces, and in some cases, thick ice shells over potential subsurface oceans. Ganymede is the largest moon in the solar system, bigger than Mercury. It has its own weak magnetic field. Callisto sits farther from Jupiter, in a region where radiation is much lighter compared to Europa and Io. Europa has a harsh radiation environment near the surface, but below its thick ice, you might get shielding from the worst of the particle flux. In all three cases, you gain something Jupiter never gives you: ground. You can build foundations, drill, mine, dig tunnels, and pile rock over habitats for shielding. You can put structures down and expect them to stay where you left them, instead of constantly fighting buoyancy, storms, and vertical mixing. Jupiter then becomes the backdrop, the anchor of the system, almost like a giant engine in the middle. Its gravity organizes the orbits. Its magnetosphere and radiation belts provide energy flows you might tap into indirectly, and its mass shapes the environment. But your day-to-day life, your actual settlement, happens on solid moons where gravity is much lower than Earth's, where you can climb out of a gravity well without needing insane amounts of energy, and where you can in principle build up a local resource base. Look at the energy difference directly. To land on and leave from a moon like Callisto, you need much less change in speed, much less delta V, than climbing in and out of Jupiter's atmosphere. The gravity on Callisto is only a small fraction of Earth's, on the order of 1/10 G. Rockets there don't have to be gigantic to reach orbit. Fuel requirements are lower, structures don't have to hold up under 2.5 G, and emergency launch systems are at least thinkable. Compare that to Jupiter. From the cloud tops, you're fighting a deep gravity well that demands around 60 kilometers per second of speed to escape, plus huge losses to drag if you start deep in the atmosphere. That's like the difference between walking up a hill and trying to blast out of a deep mine shaft with a rocket strapped to your back. From a pure energy and logistics standpoint, Jupiter loses instantly as a place for humans to live. So if you're being honest and you run a cost-benefit analysis for human settlement in the outer solar system, the pattern is clear. Use Jupiter as a gravitational anchor, a fuel source for unmanned skimmers, maybe even an energy source if you can tap its magnetic environment in clever ways. Put people on solid moons that you can slowly turn into real bases, with domes, underground habitats, and local industry. That's not as flashy as building skyscrapers in the clouds of a gas giant, but it matches the physics. And once you accept that, you see Jupiter for what it really is in the story of human expansion. Not a future city site, but something else entirely. A massive, dangerous neighbour that still plays a crucial role in why Earth exists in the first place. To really understand why you shouldn't try to live there, it helps to zoom out one last time and see Jupiter from a wider angle, as the giant that has been shaping and sometimes protecting the inner solar system for billions of years, and why that guardian role depends on it staying exactly as hostile as it is now. Here's the twist that ties all of this together. Jupiter is terrible as a home, but it's very likely one of the reasons you even have a home on Earth in the first place. Out in the cold outer solar system, there's a lot of debris, comets, and icy bodies falling in from distant reservoirs. Jupiter's gravity is so strong that it acts like a giant filter. Some objects get pulled in and slammed into Jupiter itself. Some get flung onto new paths that miss the inner planets. Some get captured into safer orbits. Over billions of years, that kind of gravitational cleanup probably removed a lot of potential impactors that could have hit Earth. You can see hints of this in real time. When comet Shoemaker-Levy 9 hit Jupiter in the 1990s, it broke into pieces and slammed into the atmosphere at tens of kilometers per second, leaving dark scars bigger than Earth. That kind of collision shows how Jupiter can act as a target, taking hits that might otherwise have gone further inward. It's not a perfect shield, some threats still get past, but statistically, having a massive planet out there changes the number and type of objects that cross Earth's orbit. That gravitational bouncer role only works because Jupiter is exactly what it is, a huge, violent gas giant with enormous mass and a deep gravity well. If you shrank it down until it was comfortable to stand on, it would also lose a lot of the influence that makes it such a powerful sculptor of orbits. The very thing that makes it dangerous up close is part of what makes the inner solar system more stable over long timescales. And that leads into a simple point people don't like to hear: too big to live on is real. All the features that make Jupiter impressive in space images, the massive bulk, the rapid 10-hour rotation, the gigantic magnetosphere, are exactly what scale up the hostility. Stronger gravity doesn't just mean you weigh more, it means a deeper gravity well that demands huge escape speeds and crushes anything that falls too deep. A bigger magnetosphere doesn't just mean more auroras, it means radiation belts that are lethal near the planet and dangerous even out at the moons. More mass doesn't just mean a bigger sphere, it means pressures and temperatures inside that turn normal hydrogen into exotic metallic states and erase any hope of a solid, reachable surface. So you get this clear split. What's good for protecting a planetary system and shaping orbits is bad for human bodies and human hardware. Jupiter sits firmly on the great for dynamics, terrible for biology side. From our distance, Jupiter is one of the most spectacular objects you can look at. In a telescope, the bands, zones, and the Great Red Spot make it look like a painted marble. In time-lapse images, you see storms drift, merge, and evolve. From orbiters, you get close-up views of cloud tops, lightning, auroras, and a level of atmospheric detail you can't get on any other giant world yet. For science, it's a goldmine, a lab for fluid dynamics, magnetospheres, and planetary interiors all rolled into one. But that same beauty is a warning label. Those multicolored bands are jet streams with winds into the hundreds of kilometers per hour. The swirling spots are storms larger than continents, powered by deep convection and internal heat. The glowing auroras at the poles are signatures of intense particle bombardment. Every feature that looks cool in a picture is backed by numbers that say, "Do not bring unprotected life here." So when you ask, could we adapt? Could life evolve there somehow? The answer from current data is harsh. The environment is too extreme and too variable. Temperatures swing from cryogenic to hotter than a star's surface. Pressures go from near vacuum to millions of bars. The chemistry is dominated by hydrogen and helium with corrosive traces. Radiation levels near the planet are high enough to kill complex organisms very quickly. There's no stable long-term niche that looks anything like the zones where we see life thrive on Earth. For humans, it's even clearer. Everything about Jupiter demands heavy machines, thick shielding, and short mission lifetimes. We already see it in how we design probes, heavily armoured, limited exposure time, and treated as expendable. Swap the probe for a person, and the same environment turns into something that overwhelms life support, medicine, and engineering all at once. So the final verdict is straightforward. Jupiter is not your future home. It's not hard mode Earth. It's a completely different category, a world built on scales and physics that do not leave room for human settlement anywhere near its atmosphere. At best, you get brief robotic passes, maybe distant crewed stations parked safely out near the calmer moons, wrapped in shielding and always treating Jupiter as something you study from afar, not something you try to tame. In the big picture, that's fine. You don't need Jupiter to be a home, you need it to keep doing the job it already does, being the massive, chaotic neighbour that shapes orbits, cleans up some of the danger, and gives you a target for missions that push engineering and science to their limits. So when you see those gorgeous images of Jupiter, remember what they really show you. Not a future skyline, but an enormous, terrifying, magnificent system that you only ever visit with robots, simulations, and equations. You look, you measure, you learn, and then you go home to the small, fragile world that is actually built for you to live on. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.